Okay, so sorry, it took me a minute to get this to link up this morning. Where we left off last time was just a quick peek at a robotic arm moving, okay? And I mentioned that we'd then start off by looking at what is definitely the best robotic arm control out there. And we'll just take a few minutes to watch these clips from 60 Minutes from about 3 years ago, 2 to 3 years ago. Okay, and this is by the Schwartz Group at the University of Pittsburgh. And then we'll go into how, now that we see how these systems work and have built up the intuition for wanting to decode a continuous arm position, we'll go into the mathematics, okay? So, yeah, maybe we can dim the lights here.
More than 1,300 Americans have lost limbs on the battlefield, and that fact led the Department of Defense to start a crash program to help veterans and civilians by creating an artificial arm and hand that are amazingly human. But that's not the breakthrough. We don't use that word very often because it's overused, but when you see how they have connected this robotic limb to a human brain, you will understand why we made the exception. To take this ultimate step, they had to find a person willing to have brain surgery to explore new frontiers of what it is to be human. That person would have to be an explorer with desperate need, remarkable courage, and maybe most of all, a mind that is game. The story plugged her brain into the computer, and this is what we saw.
I can move it up and straight down and left and right and diagonally. I can close it and open it, and I can go forward and back.
That is just the most astounding thing I've ever seen. Can we shake hands?
Sure.
No, really.
Yeah.
Like, come right over here?
Yes, you come over
Okay.
there. Grasp your hand there. There we go.
Oh my goodness. Wow.
And I can do a fist bump if you'd like.
That's amazing. What are you doing, Jan? What's going on in your mind as you're moving this arm around? What are you thinking?
Okay, the best way to explain it is raise your arm.
Uh-huh.
Good. Now,
Right.
what did you think about when you did that?
Well, not very much. I do it all the
Exactly.
time.
It's automatic.
Is that hard work? Are you having to concentrate? That will help with some of the things that Jan has trouble with.
Okay.
For example, sometimes when she looks right at an object, she can't grab it.
Okay, I'm going to take the cone away. Just go ahead and close it.
Oh, sure.
So as soon as
no
I take the
problem.
cone away, there's no problem. But as soon as I put the cone there, she can't do it.
Why
Yeah, well,
is still a mystery.
All right, well, we turn on the lights. So does that give you a pretty clear idea? I think we could maybe even argue the glass is now 2/3 full in the analogy we've been using. So here you're seeing her important comment about what she's thinking about, and I don't know what I think about when I move my arm. You just sort of do it, right? But the instructions that are used to help get these systems going and to learn these algorithms is to imagine or attempt to move your arm, okay, as we talked before. And that elicits the neural activity. We then build the tuning curves and then the decoders, and then we hook it up like this. And you can see the range of movements, not only 2 dimensions, but actually 3 dimensions, forward and backwards as well. We're talking in this class primarily about 2 dimensions to keep things simple, but it generalizes to a 3rd dimension. And then you also, of course, notice that she's able to open and close her hand grip, okay? And that's not to say that she could move individuated fingers and have all those degrees of freedom, but it definitely is saying that she could open and close, send one sort of open or close command, one bit of information, in other words, to open or close it in a very functional way. Okay? So is that that's what's working. And the speed with which you're able to do that, the way in which the arm moves relative to exactly how she wishes it to, some of those things are unclear, right? So those are really current problems in the field. And then this interesting business about the red cup. That's often confusing. So anybody want me to sort of unpack that a little bit? Yeah. So she can clearly reach out into free space and close her hand, okay? But the observation is that if there's an object there, okay, maybe even a red object or other sort of idiosyncratic sounding properties, she can bring the hand out here, but she can no longer close it, okay? And the key point here is that we've almost lulled ourselves into thinking about the motor cortex and premotor cortex as sending signals only related to moving the arm. Really not paying much attention to the fact that these areas in the brain are also responsible for many other things that are going on. Maybe they have a role in vision or in attention. It's not like it's the final output to a bus that drives a robotic arm that you might, get at Fry's or something, okay? It's influenced. The signals are contaminated or modulated by other things like staring or paying attention to that object. So what they're intimating here is that there are these other mysteries going on that we need to understand. How is it that seeing something or paying more attention to it or maybe imagining something with the object is interfering with the neural signals, changing those neural signals such that it flummoxes our decoder and it makes it unable to close, okay? So the important point there is not that it's a red object or that it's an object. It's really to sort of put just a little asterisk next to the whole topic here, just to remind ourselves that there's more going on than just reading out these purely motor signals. Yeah?
What could possibly be the difference then between that red cone and, for example, shaking his hand?
Many things. So, certainly we recognize that one's an inanimate object, the other's animate. There's a color difference. The other person's hand looks like a hand. What I'm talking about is undoubtedly coming across as, and it is, sort of these fuzzy type ideas, okay? But welcome to the brain, okay? There's nothing clearly separating these areas of vision and attention and motor. They're all in reciprocal loops, they're all in networks, so that signals in one area that may be predominantly associated with vision, like the occipital lobe, that's true, but it's not as though there aren't some traces of that visual information even in the motor cortex. And if we if we understand that better, i.e. more basic neuroscience, then we could factor that out. We could say, oh, okay, on our electrode array, we see evidence that there's actually something going on with this type of object. Let's subtract that out of our neural signals, leaving behind the types of neural signals that we've been looking at and that we're going to be working with here in just a second that are more purely motor. Okay? So it's the wild, wild west, right? This is sort of reaching back to the very beginning where we know enough about the brain to get going. We know enough about where things are organized. We know enough about the neural signals. But I wouldn't want you to come away in any way, shape, or form feeling as though we understand it thoroughly or fully. These types of mysteries just pop their heads up, right? Okay, and you can be assured that particularly in a very high visibility place where it'd be very nice to say, oh, this is really working well, you can be assured that these are actual concerns and actual problems. Otherwise, they probably wouldn't be going into them on 60 Minutes, right? Okay, which is very responsible of them. I think I commend them highly because that's helping the public understand that this is very exciting research. It's very promising, but there is still a long ways to go. Like, you wouldn't want this system today necessarily because you can open your refrigerator, but you can't you can't pick up washing detergent. So there's a lot more we need to understand. Okay, so we're sort of done with the high-level motivation, trying to understand how things work. Now let's really dive in to understanding how we're going to be looking at the neural signals, how we're going to account for them, how we're going to operate on them mathematically, so that we can actually predict exactly how this robotic arm should move or how a computer cursor should move. Okay? So let's go back. Let's go back to a slide that I showed last time, just copied in here, just to bring us back to the fundamental currency with which we're dealing. Okay? We're dealing with a bunch of neurons, and each neuron responds differently as a function of, for example, the angle that you're reaching. Okay? We know that we are sampling from a large population of neurons in such a way that we can envision having one neuron with a preferred direction here, another one here, and the more neurons we have, the better we tile that space or span that space. So we ought to be able to predict any direction that we're moving. Okay? So this is often how we plot the tuning curves, and I'm going to just change the representation in a trivial way. We're just going to go to polar coordinates. Okay? And the reason for that is that, you know, whenever there's anything circular, you have these sort of awkward tails and wraparound effects and everything. But in polar coordinates, it's all much simpler to envision. Okay? So let's look over here first of all. And let's just look at this sort of orangish, yellowish oval here. Okay? So what is going on? What's going on is we're recording from one neuron, and we're plotting on the radius the firing rate of that neuron as a function, so that's r, right? As a function of theta, the direction of reach. So you can imagine a hand right here reaching out to the right and measuring some firing rate. We could call it, you know, 100 spikes per second. And then if you're reaching up and to the right in physical space, then if we look at this, which is this neural response space, we may be getting 80 spikes per second. And when we're reaching to the left, we may get 20 spikes per second. And very familiar concept, we're just putting in polar coordinates. Okay? What this does is it allows us to think about a vector going from the origin out to the direction of maximal firing. Okay? And we know that that theta of that vector is the preferred direction. So for example, this red neuron over here, where the peak response is to the left, the preferred direction is 180 degrees. The yellow one here that we were just looking at, orangish yellow, would be 0 degrees. The blue would be 90 degrees and so forth. Okay? Now, we won't dwell on it, but these are obviously stylized. This starts to look a little bit more realistic, okay? Where, you know, nothing is perfect like this in measurement land, certainly not in biology. So you may get these little kinks and maybe even double lobes, and some may be narrower, some may be wider. But to first order, let's say that there's some nice monotonic curve here, and we can characterize it by this vector pointing in the preferred direction. Okay? So then what we have across a population of neurons is a whole set of different vectors pointing in that preferred direction. So let's look at this one here. Okay? So this is preferred direction 1. Okay? So this is basically reflecting a neuron who has a preferred direction to the right. And let's consider that to be a unit vector. So it's of unity length. Okay? Now another one, this orange one here, may have a preferred direction up and to the right. So we can call that preferred direction 2. Okay? And so on. So dot, dot, dot. Okay. Now, the whole rest of today's lecture, or the whole rest of so-called population decoding, is absolutely trivial. It's absolutely simple. And I don't want us to get lost in the math. So I'm going to try to make the intuitive argument right here. And we're going to pause and just make sure that it makes sense to everybody. Because if we can do that, then the rest, yes, there will be nomenclature. We'll get caught up a little bit in, okay, is it a column vector, is it a row vector, and so forth. But you'll have the guiding intuition. Okay? So let's say that we characterize this neuron as a unit vector to the right. Okay? But on any given trial, let's say that we measure that firing rate as being 100 spikes per second. Okay? We can weight the length of that arrow by the firing rate. We can multiply this rightward going arrow, we can multiply it by 100, and we would have a very long rightward facing vector. Okay? Now let's say that for that same reach, okay, that we are trying to estimate which way you're reaching, we're recording also from this orange one. Now if you're really reaching to the right, this right here is the firing rate of this orange neuron when you're really making a reach to the right. Agreed? Okay, and I don't know, let's call that 60 spikes per second. Okay, so this to the limb. So there is that delay, often called lag. We haven't really talked about that yet. We've talked about the neural activity being exactly synchronous, simultaneous, it's a better word, with the measurement. And that's basically the approximation we're going to need. But indeed, neural activity happens about 150 milliseconds before the arm starts moving because of conduction delays right down the arm, as well as getting the muscle spooled up. But that's not related to this choice. So what happens, yeah?
So let's say less than 20 milliseconds might be not enough time
Yeah.
to get enough spikes, but
So then it's noisy.
right.
Yep.
More than that, you might not get good enough resolution.
Perfect. Exactly. Yeah. So does that make sense? So if we go down to, we know what happens at 1 millisecond resolution, where we may, I want to know where that arm is every single millisecond. It sounds like a great engineering spec, right? But fundamentally, we know that at 1 millisecond, we're just going to get a 1 or a 0 because of refractory period. So 20 milliseconds is, in practice, enough time, okay, for a given neuron, and across roughly 100 neurons for you to get a pretty good estimate. And if you went too long, 200, 300, 400 milliseconds, watch my arm here. Okay, that's pretty quick. In sub 1 second, I can move quite a long distance. So I want to actually be able to reconstruct where it is, many points along that, and with a certain velocity. Okay, technically speaking, what you need to do is you need to look at the frequency spectral content of the movement, and then make sure that you're sampling fast enough as per Nyquist's theorem. That's really what's going on. Okay, because otherwise, if you measured it only every half second, you're undersampling, and you could never theoretically reconstruct the actual arm movement. Okay. All right. So I think we've also covered a little bit of this now, but fair enough. So as we're focused on spike-based decoders, the neural spiking activity, this yk of I, is typically the bend spike counts. Okay, we just talked about that. And this is computed by counting the number of spikes, okay, neuron I emits in a non-overlapping interval of delta t. Okay, so you might think, well, wait, I want a little bit more smoothing. So in time, I may take 20 milliseconds, that I may skip over only 10 milliseconds and take 20 milliseconds again, and so forth. And you could do that. Operationally, you could certainly do that. But what you're effectively doing by having overlapping bins is that you're smoothing the data. Okay? And for many algorithms, you want to make sure that you're not performing that smoothing step there. You're, in fact, adding that type of smoothing or denoising operation explicitly and later in the signal path. Okay? So the spike interval delta t, I guess now that I've drilled 20 milliseconds into your head, is typically several tens of milliseconds. We're just going to go with 20 milliseconds. And by binning time and counting the number of spikes within those bins, one's really estimating the underlying firing rate, right? Okay, so the time length of the data sampled in the matrices x and y, overall, we've already gone through this, is some cap tau k times delta t. Okay, so delta t may be 20 milliseconds. The total length of the data may be 10 minutes. And this tells you how many of those independent time bins there are. Okay, so if it were me looking at these slides for the first time, in case it's helpful, I would say, all right, enough already. It's going over and over the same things, and I think that's how it should feel, right? The attempt here is just to be very clear. The attempt is just to be very clear, but there's nothing deeper than we're going through. This is all basically just laying out the framework. Okay? Now, we're almost to the algorithm, but we already know what the algorithm is going to do because we've added vectors head to tail. Okay? So the algorithm, the population vector algorithm, okay, or in this algorithm, x of k, again, the kinematics, okay, is typically the velocity of the prosthetic device. So we've talked many times about wanting the position and the velocity. But in practice, often, not always by any means, often it's just the velocity that we're after, and that's what we'll really focus on in class. And the reason for that is you can always get position by integrating velocity, right? So if I know at time step 1 I was moving in this direction at that speed, then of course I know where I am, right? So you go ahead and move the prosthetic arm there, and then physically the arm is there, so you're keeping track of position just by physical location, or you could have another integrator going, okay? The activity of the ith neuron, okay, at any time can be described as a function of the kinematic variables. This is simply the tuning curve, right? So yk of I, right, the firing rate, y, at time k of the ith neuron is simply some function of the kinematic variables, okay? Number 3, so in this way, a tuning curve can be built where the average firing rate of a neuron is computed for different reach directions, right? We know we must do that. That's simply saying, you know, please reach to the right. Okay, I reached to the right. I measured what that movement was like. I measured the neural activity. There we go. Now please reach up, okay? And in practice, that often takes on the order of 5-10 minutes, because what you're going to want is you're going to want to reach in a certain number of directions, for example, 8. Okay, you're not going to spend all the time to reach, you know, to the right and then 1 degree up and 1 degree up. We're just going to take a few measurements, and because we know tuning curves are smooth, again, sampling theorem, we only have to measure it a few places, and then we can confidently interpolate. Okay, and fitting the cosine function is that interpolation. Okay, and we don't want to just reach to the right or up once, because we know about noise, we know about the Poisson distribution. We're going to want to, in practice, maybe have 10 repeats, or so-called replicates. Okay, and we're probably going to not want to do that in order. Reach right, reach upright, reach up, because when you do things in order, it could influence. You want to do it randomly, so that the only thing that you're really pulling out of that tuning curve is the reach direction. Okay? So the fourth is the firing rates are subsequently interpolated. We talked about this across reach direction with one period of the cosine wave. Okay? So yki is going to be proportional to some cosine. We've worked with this before, so I won't belabor it. The direction, okay, for which the neuron I is modeled to fire most strongly is the preferred direction. We talked about that graphically, right? Hopefully that graphical intuition is now fusing together with this. Okay? And we're going to denote a unit vector in that direction as some vector d. Okay? Right? So it has some x component and some y component, and therefore it's a vector, right? And the contribution of each vector d, each unit vector to the decoded kinematics, is this estimated xk, okay? And it's linearly proportional to the firing rate of the neuron. Okay, here's the equation, okay? Should have a soundtrack. Da-da-da. Finally, the equation after all that. Okay, so let's unpack this equation, right? First of all, xk hat is going to be our estimate of how the arm should move in horizontal and vertical, at some horizontal and vertical speed at that point in time, k. Okay? And you can see the dependency on the unit vectors for each of the eye neurons, right? Remember when we were adding those vectors head to toe? So we have to have those. And it's going to have to be, of course, dependent on the neural firing rate that's observed. Okay? We'll talk about the A and B parameters, or the alpha and B parameters in a second here. But basically, we see the firing rate being multiplied by the unit vector. Right? That's that scaling that we talked about. Okay? And then we're going to sum up across all those vectors, and that's the adding, the vector add, right? The head to toe add. Okay? So what is the BI term here, first of all? So BI is an offset term, typically the mean firing rate of neuron I. Okay? such that when yk of I is less than bi, the neuron contributes in the movement direction negative di. Okay? So basically, if this is the average firing rate, if your firing rate is below average, this turns into a negative direction, so you're actually flipping the unit vector. Okay? Fair enough. Okay, nothing deep there, just a reminder. Now, what's the variable alpha I? This down here. Okay, the variable alpha I for each neuron is a weighting term typically chosen to be the modulation depth of the neuron or a variance normalizing term. Okay, and this is the answer to the previous question, which is basically saying if one neuron fires between 0 and 500 spikes per second, right, we want to think in terms of what percent, more or less, of that firing rate range should be multiplied by that unit vector so that it is voting equivalently to another neuron that may be firing between 0 and 50 spikes per second. Okay? So what's the term C? Okay? The term C is just a constant to make the sum proportional to the speed. Okay? So we have the right units here, but there's always going to be some, in a sense, calibration factor. Okay? Now if we define some Z, okay, we're just going to do this so we can write this a little bit more cleanly. Okay? If we define some Zk of I as Yki minus Bi, okay, times alpha I to be the normalized firing rates, as we were just talking, then the preferred vector algorithm, population vector algorithm, can be written as xk hat, okay, the Cn term here, and then simply the normalized firing rate times d. Okay, and that really is the graphical thing that we went through up front. So convenience, we can also define the vectors zk and the matrix cap c. Question?
So what is modulation depth?
Modulation depth would simply be the maximum minus the minimum firing rates. Yep, some overall amplitude. Oh. That's it? Okay, so how does this mesh up with reality? Okay, not reality like could we do better, I'm meaning reality like homework, okay? So the thing to do next to really have this sink in, right, is what's in the homework, okay? And what's in the homework is to start working with this, right? Fitting these curves, doing some estimates, and what you'll find is that, and hopefully this is satisfying, hopefully this is one of those like really fun moments when you start seeing it happen, is that you'll just have all this sort of chicken scratch coming at you, like, you know, all the spike times from all these different neurons. And when you go through these different steps, right, which you'll then implement in MATLAB, okay, not hard, just follow the recipe, okay, at the end of the day, you'll get these pretty satisfying looking plots where you can plot in vertical and horizontal, you know, it's an XY plot, how the real arm was measured to be reaching. This is from monkey experiments that we perform in our lab, okay, some of which Jonathan performed himself, okay. And then, you know, in another color, you can plot the estimated, okay. And it won't look identical, right? It can't look identical, but it'll look really rather similar. And hopefully that similarity and just sort of seeing it all work is one of those, I don't want to call it a magic moment, but you know, one of those fun things that you'll remember, and that's the hope. Okay? So I think when you turn the crank through all that, that'll help bring to life what otherwise is just this, you know, boring set of terminology and simple equation, you know, been beating on this simple thing too much. What will then start Wednesday for handout 12 and handout 13 is to say, you know how this works. This was historically the original decode algorithm. It makes, you know, very strong intuitive sense. That's how we can build off of it. But let's really come back and try to do a much better job. Okay, that will be more involved. This is the Kalman filter I've been talking about. But hopefully, by having first seen what you can do and what the shortcomings might be, it's easier to be motivated to understand the power that these extra algorithms are giving. I think there was one question.
How come the equation the one ZK are different?
Sorry, I see this. And then down here,
Yeah. So
oh, is the n in the wrong place?
and alpha.
Well, no, the alpha, because zk is up here, right?
In both cases, there's just a division missing.
I'm sorry. Yes. I'm sorry. So there should be a division here, and there should be a division here. Yeah. Sorry. Typo. My fault. Good catch. Intentionally placed. Okay. Have a great weekend. Long weekend.
Have a quick observation that we have them back here.
Yeah.